Bismillahirrahmanirrahim. In the last lecture, we have discussed about what is electric potential energy, and equipotential surfaces. Now, in this session, we will talk about how we can calculate the potential from the field. As you can see in this figure, the blue lines represent the electric field lines, and a positive test charge Q naught that moves along the path I to F. The positive test charge is placed in the electric field lines, and this is moving from by following the path I to F. So at any point within this field, when the test charge is moving, there is a displacement ds, small displacement. The force acting on the test charge is F is equal to simply with what we have learned before. We will apply that thing. Q naught E. The force exerting on this test charge is F is equal to Q naught E. Now the displacement is ds. So what does the work done on this test charge is dw. Force into displacement, we already know that the work is equal to force acting on that particle into displacement. Okay, so by putting the value of F, Q naught E, these are little calculation derivations. Okay, E dot ds. So if we want to calculate the electric field through this whole path from I to F, so we have to integrate the work done. dw is equal to integrating from I to F, Q naught E dot ds. Q naught is constant, so I will take it out from the integral. If we solve the integration, Q naught I to F ds. Limits I to F E dot ds. Here is small dot. We know from the previous lecture that change in potential energy, I'm going to write over here. The change in potential energy is equal to Vf minus Vi, that is equal to work done per unit test charge. Is that the negative of the work done per unit charge? So instead of W, I replace Q naught into Vf minus Vi. Q naught IF E dot ds. Now we all know that the electric field is conservative. What does it mean? So all it gives the same value if by following the all paths, any path within the electric field. So uh, Q naught, I'm going to cancel out the Q naught. VF is equal to minus I to F E dot ds. So where Vi gone? I'm also going to skip this, drop this subscript F and write it as V is equal to minus I to F E dot ds. Why I did this? Because I am taking the potential V at any point F in the electric field relative to the zero potential. Okay, starting from the zero potential to the final position at some electric potential V. So Vi is equal to 0. Okay, at this point. So the final potential is V is equal to minus I to F integral E dot ds, gives us the potential V at any point F relative to the zero potential at infinity. ठीक है, Vi at infinity. Okay, so we have to remember this equation for the next. The next is potential due to a point charge. Now we use the same equation. V is equal to minus I F E dot E S following the path to drive the electric potential at some distance from the positive charge. Okay, you can see here that the positive point charge Q produce an electric field. This positive point charge produce an electric field E, and an electric, we have, what we have to do, we have to calculate the electric potential due to this point charge. The point, let the point charge, let the point P is at a distance R from this test charge. So everything we have in our mind is that let us consider from where this test charge, we have to place a test charge Q naught from point, which we will consider that it is moving, move a point test charge Q naught from point P to infinity, mean ke we have to find the electric potential at point P, and we play and we consider that, we suppose that the test charge Q naught moving from point P to at infinity. Okay, because the path we take does not matter. Let us choose the simple one, a line. Let this is the most simplest path, it is a straight line. Okay, so here is this. This is the positive charge. Electric field lines are radially upward. Okay, and the distance, the charge is also moving in straight line. So that E dot ds is equal to E cos of theta ds. Theta is angle between E and ds. It is 0 because both are parallel. So we have this e dot skip हो गया, dot खत्म हो गया, it is equal to ds. By using this equation, vf minus vi is equal to negative, और अब देखें, I will replace these limits I to f with r to infinity. As I I said before that this test charge is moving from point P, which is at a distance r from this test charge, from this point charge, from P to infinity. Okay, the distance, but the path is following by this test charge is from r to infinity. E dot E dr. So Vf is equal to 0 because at infinity we have learned that at infinity potential is 0. So Vf is equal to 0. We are left with minus Vi is equal to minus r infinity E dr. ठीक है. Why I change ds to dr? Because the path is radial, and so we can write dr instead of ds. ठीक है, रेडियल पाथ है तो हमारी कैलकुलेशन में इजी हो जाएगा. So we all know that E is equal to 1 over 4 pi epsilon naught q over r square. So V is equal to, by dropping this subscript, r to infinity q by 4 pi epsilon naught 1 over r square dr. By solving this integration, constant term will come out. Q over 4 pi epsilon naught r to infinity 1 over r square dr. Again, by solving this, we end up with the result will 1 over 4 pi epsilon naught q over r. So V is equal to 1 over 4 pi epsilon naught q over r. Did you notice that this is potential due to positive point charge? Recall the previous lecture. The positively charged, where we have discussed that a positively charged particle produces a positive electric potential and a negatively charged particle produces a negative electric potential. So this is due to the positive point charge, and we end up with the electric potential having positive value. Here is a computer generated plot of the electric potential VR due to positive point charge. These are x-axis, x, y, and z-axis. Okay. Electric due to positive charge, positive test charge are located at the origin of xy plane. Okay. So the potential is plotted vertically due to positive test charge. It should be positive. It is pointed vertically here. The density of electric potential is, you can see that the magnitude of V is increases as the magnitude of V is increases as R approaches to 0. ठीक है, जितना ये रीजन के करीब होगा उतनी डेंसिटी इसकी ज़्यादा होगी. According to according to this equation which we have learned, Q over V is equal to 1 over 4 pi epsilon naught Q over R. According to this equation, if R approaches to 0, electric magnitude of the electric potential is up to infinity. But here is the figure shows some boundaries, finite boundaries, but it should be at infinite values. Okay. Next, I want to discuss the electric potential due to an electric dipole. So we try to calculate the electric potential due to an electric dipole, just like before we did in chapter number 22 to calculate the electric field due to a dipole. Okay. Using equation, I think by using equation V is equal to, if I write over here, V is equal to I is equal to 1 to and 0. What does it mean? It means we have calculated this for a point charge. Okay, if we have more than one charges, then of course we will apply the superposition theorem, apply the summation of electric potential due to all charges, and we write it like 1 over 4 pi epsilon naught summation I is equal to 1 to n qi over ri. N क्या है? N is point charges. Okay. So if we use this equation, and now I am talking about the dipole. Here is dipole. We are dealing with more than two charges. Okay. Sorry, more than one charges. Okay. So what we will do, we use this equation again. I is equal to 1 to 2 V R. So potential due to positive charge plus potential due to negative charge. It should be written as 1 over 4 pi epsilon naught Q over R plus minus Q over R minus. So coming toward this figure, two charges, opposite charges are separated by small distances make a dipole. What I have to do? So what we have to do, we have first what we have to do first we have to choose a point where I want to calculate the electric potential due to these charges. I choose the point P over here. Why we choose point at this place? As naturally occurring dipoles are quite small, so we're interested only in the point that relatively far from the dipole. Okay, mean if we want to apply the condition r very greater than t, the distance between this point and the dipole axis is very greater than the distance between the two charges. Okay, why I want this situation? To make our calculation more easy, and use some approximation under the, I can easily use some approximation under this condition. Okay, what is that approximation? Is if you look into this, if point P is very far from uh, this dipole axis, okay, then how my previous picture will look like. Okay, these indicate that point dot indicate that the point P is very far from the dipole axis. Okay, now our picture look like this one. Distance from the positive charge of the dipole is r plus, and distance from the negative charge of the dipole is r minus. Okay, we will use this triangle. Here is r plus, r minus. How I could get the this value? Okay, this point is little r minus is greater than, is more away from as compared to r plus. ठीक है, r minus is greater than r plus, so the जितना उसका इंक्रीमेंट है कितना ग्रेटर है, दैट इज इक्वल टू r माइनस r फर्स्ट. ठीक है, if I draw a vertical line, a projection on r minus, I will end up with a triangle like this. ठीक है, this is the theta angle, r minus r plus. Here is distance d. We don't know about this. Okay, the trigonometric ratio dealing with hypotenuse and the base is cos of theta. Again, the very friendly cos of theta. Cos theta is equal to base over adjacent, base के r minus r plus. ठीक है, here is minus. Okay, divided by adjacent in d. So I have value r minus r positive is equal to d cos of theta. ठीक है, and another approximation, both are r minus dot r positive is equal to r square. This will make our calculations very easily. Okay, and what we have the potential now coming toward by putting these values in above equation. Where is the above equation? This one. I'm going toward the green here. These equations. Okay. If I put these values in above equation, we end up with V is equal to Q over 4 pi epsilon naught d cos of theta over r square. So again 1 over 4 pi epsilon naught q d cos of theta over r square. What this qd is? This is the magnitude of the electric dipole moment. E is equal to qd. So by replacing this qd with p, p is the magnitude of the dipole moment over r square. So the electric potential due to a dipole is given by this equation. The vector p, here p is a vector quantity, is directing along the dipole axis from the negative charge to the positive charge. Okay. Next, what is induced dipole moment? You have learned about the permanent dipoles. The very famous example is oxygen water molecule. These are, and there is some non-polar molecule whose where the center of these non-polar molecules are consigned with each other. Center of positive and negative charges are consigned with each other. So there is no distance between positive and negative charge to make them a dipole. If there is no dipole, there is no dipole moment. But if I place this non-polar molecule in an electric field, what will happen? What will happen? You can see that the electrons are negatively charged, so, and the negative charged element will move opposite to the direction of electric field, and so the electron will moves in the opposite direction of the field, and and this shift set up a dipole moment p that points in the direction of the positive charge. I said that the dipole moment direction of dipole moment is from negative to positive charge. So when I place this non-polar molecule into an electric field, the electron move in the opposite direction of the electric field, and the dipole is induced in this molecule. Okay, which will set up a dipole moment that points in the direction of this field. This dipole moment is said to be induced by the field, and the atom or molecule then said to be polarized by the field. What happened when the field is removed? The induced dipole moment and the polarization will disappear. Okay, so so moving toward the next topic, that is potential due to a continuous charge distribution. Potential due to a positive continuous charge. What is continuous charge distribution? Continuous charge distribution means charges are uniformly distributed either, we have learned before, either on the thin rod or a charged disk. So what do you think, that can we use this equation of summation vi is equal to sigma phi to n I to n, what was that? Qi over r. Can we use this equation to find the potential due to continuous charge distribution? You can think that there is so many charges which are distributed over the surface of the thin film or a thin rod or a disc. Can we use this summation rule to find the charge potential due to continuous charge distribution? No. Why? Because the charge are uniformly distributed. Instead, we will calculate by using the for line charge. For line charge, we will use the linear charge density lambda as a function of lambda into dx dq, and then we use the same formula v is equal to 1 over 4 pi epsilon naught dq over r to calculate the potential due to this continuous charge distribution for line of charges and for disk. Okay, for charge disk. I leave this exercise for you to drive for both formulas because we have discussed before in by using the same mathematical steps in chapter number 22. So I left these two little derivation by using the same concept we have discussed now, for you to solve, and we will discuss in our question and answer session.